Today's lesson is on area and Riemann sums. You're going to hear his last name pronounced differently here and there, but I do believe that, well, he is German, and I do believe in German this is pronounced Riemann, so that's what I usually go with, Riemann sums, and that's what he looks like. Okay? Here's what he tells us. One of the things. Well, before I get into that definition, think about back in geometry, right? Say I gave you like this odd shape. No, that's not really there. I'm trying to draw a rectangle here. Say there's a rectangle there, and then you had some odd shape here, and that was a semicircle. And then up here you had, say, a triangle, right? And I said, what's the area of that? You would do, I think most of you would know, you would find the area of this triangle, right? You would find the area of this rectangle, and then you would find the area of this semicircle, if it was a semicircle, and you'd add those three areas up. Well, that's the concept here. A Riemann sum is an approximation of the area under a curve, and how we're going to do that is we're going to divide that region into multiple simple shapes. And we focus on rectangles and trapezoids, but it's the same concept whether you have semicircles and triangles and all that fun stuff. Well, let's look at this now, because there's a few ways we could do that. There's that definition. There's good old Senor Riemann. Now here, notice how you could, if you're going to break this, so I want to find the area in between, it doesn't matter what these are, I'll just call it A and B, right? There's A and B. And, well, I have choices, right? If I want to find the area, if I'm going to break up into rectangles, I have a couple choices here. There's A and B. I could decide that when I put this point into my function, I'm going to use that y value, right, that height. That would be the height, and this would be the base, right, just to show that. And then I could be consistent, and I could use the left side of each rectangle to find the height, right? Because that would be the height of that one, the height of that one, the height of that one. And this is known as a left Riemann sum. Let's go over to the right one here. So our other choices, let me change. I could, over here on the right, I could, instead of using the left side of the rectangle, I could go to the right side of the rectangle, plug that x value in onto the function and get the y value, right? Because the y value would be the heights here, the height of this one, the height of this one. If I go to the right side and stay consistent, what do you think this one's called? This one is called a right Riemann sum, RS Riemann sum. And, well, as you can see, sometimes it's an underestimate. This one looks like it's a little bit lower, right? It's not always a left one. It depends on which way the curve is going. But sometimes it's an underestimate. It's below. Again, depending on the curvature, a right one could be the overestimate. It's not always. Depends on the curvature. But sometimes you're over. And a good way to split the difference here is you could use what's called the midpoint Riemann sum. And, well, as you can imagine, instead of using the left or the right endpoint, what you do is you find that middle x value right there, and you use the midpoint, kind of splits the difference, right? It's not as much under, it's not as much over. And let me just keep drawing this in. I'll do this one in green. So there would be the midpoint. There would be that x value you're looking for. And there you go. All right, so there's in green is the midpoint. Kind of splits the difference there. So that, hopefully that makes sense, right? If you need to pause and copy that, please do so, because there's a lot of information in that graph right there. But if you're also looking for some definitions, like, well, what exactly is this? What exactly is that? Well, here, these are, I took these definitions off of Khan Academy. I'm going to give credit where credit's due, of course, but I needed to save time. This is due, sometimes you got to get the video done, so thank you, Mr. Khan. Here's definitions for left, right? So for the left Riemann sum, we approximate the area using the rectangles. Usually it's of equal length. I'll talk about that. Well, I kind of mentioned that before. It depends if you're given a table or not. Where each height of the rectangle is equal to the value of the function at the left endpoint of its base. And that's kind of what we drew here. The left side, take the height. The left side, take the height, etc., etc. Over here on the right side, in a right Riemann sum, let me make that a little bit bigger. In a right Riemann sum, the height of each rectangle is equal to the value of the function at the right end of the base. So what you do is go to the right side of the base there and pull that over into the function to find the height and then of course the midpoint, you're basically splitting the difference. It's the height of each rectangle, and you're using the value at the midpoint. So you find the intervals. In this case, you have 4 subintervals. You take the midpoint of each subinterval, and as I drew before, it would kind of be right there and kind of right there, and there you go, okay? I will only make a brief mention about the trapezoidal sum, since I kind of did mention it right here. We have a whole lesson on this coming up, the trapezoidal sum, but or you could break it up into trapezoids, and quite honestly, this is your best bet, because if you can make make trapezoids, right? Well, look at how you can follow the curve. Today's lesson, we are strictly focusing on the left, right, and midpoint Riemann sums using rectangles. Now I'm going to focus on the one of these graphs to show you how we set this up. Goodbye, Mr. Riemann. So let's just, I think my first example is a left Riemann sum, so let's use this graph to get the visual. So I did say that here we have 1, 2, 3, 4. We have 4 rectangles, and this is the number of subintervals, and that's gonna be the letter n. I'm gonna call n, let n be the number of subintervals. Now, if you think what those subintervals are, well, since we're dealing with the x-axis here, right, I don't know what the breakout is here because, say the number of subintervals is 3 or 6, but regardless of what it is, in this case it's 4, we have a change in x, right, delta x, because this is the x-axis. So if we're going from here to here, this is our change in our x values, right? That's the delta x, change in x. And then we would, since we're doing the left, we would take whatever this x value is. Since I started with a, this right here, well, that would be f of a, right? Whatever that value is. And then whatever value that is, that would be f of whatever that x value is, etc., etc. And then that would be the height. These are going to be the heights, if you will, right? Heights of the rectangles. Same thing over here. What about the delta? So that's how we're going to find the heights. But what about the delta x? Well, here's how we find the delta x. Delta x. And we're in calculus, so I could call it Greek delta x or Roman delta x. But the change in x, well, if this right here is your a value and this is your b value, right? If your interval is going from a to b, well, what you need to know is how long is that interval? What's the length? Well, how do you find the length of it? Well, I'm going to take b minus a. That's going to give me the interval between there. And, well, if I want to break it up into 3 rectangles, I would divide it by 3. If I wanted 4 rectangles, I would divide by 4. And since n down here represents the number of our subintervals, this is how you find your delta x. I kind of put that in parentheses so it makes a little more sense in your notes. So think about this now. If I'm not going to get into sigma notation, but hopefully you've seen that along the way. I'm not out to confuse you, but that's a sigma. That's a Greek sigma, and the S, it stands for sum, right? And you're going to sum a bunch of these areas of these rectangles. I'll just do that for area of rectangle. That's really what we're about to do right now. So, well, that's the same thing as this. If you're going to take the sum, you're going to sum up a bunch of rectangle areas. Well, what's the area of a rectangle? You're going to sum up a bunch of these things. You're going to do, well, it's base times height, right? Now I'm simplifying. I'm really oversimplifying this sigma notation. I just want you to get the overriding concept here of what we're doing. So don't sue me on this sigma notation. Well, the area is a bunch of these base times heights, right? Now, what represents the base? Well, the base of these rectangles is going to be our delta x, right? That's a sigma. And the heights, well, we said the heights of these are going to be the f of x, right? You plug in the x and you get the height, the y value. Well, this is sort of Greek notation right here, right? I have a sigma and a delta and all that. Let's rewrite this in Roman notation. So sigma is an S in Greek, and that's your Roman S, and, well, that's where the integral symbol comes from. You're summing up a bunch of things. And since you know multiplication is commutative, it doesn't matter which one comes first. So what if I were to put the f of x times delta x, and since we're writing it in Roman notation, I'm going to write the delta as a d. Look at what we got there. Doesn't that look familiar? Now, regarding notation, if I'm going from a to b, well, I need to let you know what that interval is, right? So if you're starting at a and going to b, That's what these intervals, that's what the letters stand for here. The bottom one here is your beginning interval of the interval, and the top one here is the end of your interval. So you know where to start and finish. Since we're doing approximation methods, we'll consider what this equals now. So in our case, we have 4 rectangles, right? 4 subintervals. So this equals, well, you would have the f of x times dx of the first one, right? The base times height of the first rectangle. That would be rectangle 1, right? And then you're going to add to that, the base times height, or the f of x times dx of rectangle 2. And then you're going to do the same thing for 3 and 4. You have base times height, and that's rectangle 3. And last but not least, you're adding, what is that, f of x times dx of your rectangle 4. Sometimes the information is given to us in a table, an XY table. So let's do one like this one first. So we have selected values for a function given in the table. What is the left Riemann sum? So we're going to start with the left. Approximation for this integral right here using 3 subintervals. Okay, so we have 3 subintervals. Our n value is 3. And so when you're giving a table of values, I would highly recommend start by graphing what they give you. So let's do these xy points, right? We have 4 xy points. Let's graph them. We have 4, 3. I have 4, 3. And then we have 7, 4. Okay, 7, 4. Then we have 10, 7, 10, 7. So that's 9, 8, 7's down here. And then we have 12, 10. 12 is over here, and 10 is over here. Okay, let me just make sure I did that right. So this one is 4, 3, and that's 7, that's 4. And then I have 10 goes over to 7, and then 12 and 10, so that's 12, and yes, okay. Now, since those are the only points we have to work with, we have to use what we have. So if I connect the dots, the graph might look something like that. And we are dealing with 3 subintervals. Well, I'm going from here to here. That's the beginning and the end point, right? We're going from 4 to 12. And they're telling us 3 subintervals. Well, since we only have these 4 points to work with, I have to work with the information I have. So I have to break it up this way. Okay, so it kind of dictates what your delta x is. Sometimes it's the same. In this case, it's not. You go with what they give you. So this one, the delta x for this one is 3. This one, the delta x is 3. And this one, the delta x is 2. All right, so that's the basis of our 3 rectangles. Now for the heights, well, if this is the left endpoint we're doing, I have to use the left endpoint. And that's going to give me a height of 3. If I use the left endpoint, well, the left endpoint for the second one is going to have a height of 4, right? This is a height of 4 over here. I'll do it over there. And then if I'm using the left endpoint, well, the left endpoint gives me a height of 7, right? That's 7. So the area of this one is going, the area of first triangle is going to be what? 3 times 3. And the area for this one, the area of 2, that would equal, what is that? That's going to be 4 times 3. And then the area for this last one right here, the area for that one is going to be 7 times 2, right? Base times heights there, height times base. Okay. Here's how I would write it up a little more formally. I'm looking to answer this question right here, okay? And that equals this. Well, I have 3 subintervals. So I have to add up the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. And I kind of showed you over here, well, you know, you're summing up, this is going to be f of x times dx. And, well, actually, let me get more specific. This is going to be f of 4 times dx plus this is going to be f of 7 dx. And that's going to be f of 10 dx. Because f of 4 and f of 7 and f of 10, those are the left sides of the rectangle. I got the answers over here. Well, here, let me do this. We have these over here, I already said. So this right here, that's going to be 3 times 3 plus 4 times 3 plus 7 times 2. And that's going to be 9 plus 12 plus 14. That's going to give you 35. So there's 35 square units, approximately. It's an underestimate underneath that curve. Now, what if they did up here ask you for the right Riemann sum? Okay, I'm just going to kind of show you, not do the whole thing, but show you what would you do if it said the right Riemann sum. Well, the right Riemann sum, you're going to do this. Instead of using the left side of the rectangle, you're going to go to the right side of the rectangle. You're going to plug that in. That one right there is 7, so what you're looking for up here is f of 7. And then you would go over. Then this one is, well, that's x equals 10, so this up here, that's f of 10. You're going to use that and go over. And then over here, the right side is f of 12, right? So this is f of 12. You're going to plug that in. That's your height. So what would change over here is your first one would be using the right side, which is f of 7. This one would be f of 10. And then this one, the right side would be x equals 12. So you want the height is f of 12. Okay? You would change the heights here, and then you would get your answer. If you want to try it, I know the answer comes out to be 53. Okay? It's an overestimate. It comes out to be 53 if you want to try it. Let's take a look at this one now with a table. So we are given selected values, and we're asked to do the midpoint Riemann sum. Okay, midpoint, let's do that one. Here is what they're asking. We want to start at 0 and go to 12, and we want to find all the areas of the rectangles, f of x times dx, with 3 subintervals. Our n value is 3. Now notice how they give us a lot more points. So here's how you would handle this. Let's graph the points. I have them already here. And if I wanted to kind of give myself a better visual, you don't have to connect the dots here, but I'm going to just kind of like give myself a visual here. So say the graph does something like that. We're asked to break it up into 3 subintervals. Well, why don't we do this? I said that the delta x is going to equal b minus a over n. So if we know that it's ending at 12 and it's starting at 0 and we want to divide that by 3 subintervals, do you see how our change in x comes out to be 4? So let's do a delta x. We're starting at 0 and we have to end at 12. Okay, so let's break that up into 3 subintervals. If I go another 4, it brings me to 8. And if I go to another 4, it brings me to 12. Perfect. All right, so our dx is 4, right? For all of them, dx equals 4, dx equals 4, dx equals 4. But since we're asked for a midpoint, well, conveniently, look at that. They gave us the values that we need, because this midpoint, right, if it's 4, you want to go 2 this way and 2 that way, you're in the middle. If you go 2 this way and 2 this way, you're in the middle. 2 this way, 2 this way, we're in the middle. This y value right here is what f of 10 is, and this is the midpoint we want right here. That is f of 6. And the midpoint for the first one is f of 2. So now this is what the rectangles would look like. With the height, we're using the midpoints. So now we're going to go up to here and use the midpoint for the height. And then go up here and do the same thing. Use the midpoint for the height. So the answer to this, going from 0 to 12 of these f of x times dx's, well, we have the first one would be f of 2 times dx. The next height would be f of 6 times dx. And the last one would be f of 10 times dx. That would give us the height and the bases. The values are given to us here, right? 2 f of 2, 6 f of 6, and then 10 f of 10. So the values, f of 2 is 4, the dx is 4. F of 6 is 8, the dx is 4. F of 10 is 13, the dx is 4. Multiply these and add them up. We got 16 plus 32 plus 52, and when you add them up, you get a nice even 100 square units. Sometimes they don't give you all the numbers you need in a table, but rather they'll give you a function and you can figure out the values on your calculator. So here we're given, we want to do 5 subintervals, so our n value here is 5, and here's a function we have, okay? And it says equal lengths. Okay, so equal lengths means in order to find our delta x, we're going to do b minus a divided by n, which in this case is going to be 3 minus 1 divided by, we have 5 subintervals. Okay, it looks like it's going to be 2/5. Well, I'm going to make it simple. 2/5 is the same as 4/10, and why don't we use a decimal? So 4/10 is the same as 0.4. So our dx is 0.4. And as you can see, I guess I should have done this. I should have made this little squiggly line here because it's not the same interval. I'm starting at 1. So from 1 to 3. And our interval is 0.4. So if we're going 1, if we're starting at 1, then you're going to 0.4, 1.4, add another 0.4, add another 0.4, add another 0.4. And as you can see, if you add another 0.4, it ends up at 3. For left Riemann sums, we want to use the left sides. So that means for the height of the first one, we need to do what f of 1 is. The next one would be f of 1.4. The next height is going to be f of 1.8. And I think you get the hang here. I'm just getting very sloppy here. Sorry. F of 2.2. This would be f of 2.6. Let me make that nicer. And we just determined that the bases here, the dx's, are all 0.4, right? This is going to be 0.4 and 0.4, and there you go. So if we're going to add these up, this is what it's going to look like. Adding up from 1 to 3 of this function times dx is going to look like this. We have f of 1 times dx plus f of 1.4 times dx plus f of 1.8 times dx plus f of 2.2. Make that smaller. Times dx. And then we have our last one, f of 2.6 times dx. Now you're also going to see this written like this, because if you notice, there are, I don't care how you do it, but they all have a common factor, right? They all have the dx. So you could do this also. You could just find the values. Well, here, let me write the values. Well, here, I guess I'll just do it this way. So what I'm doing is I'm just taking out the one common factor of dx, and you might find this a little bit easier. And then you add all those up, and then you just multiply it by the 1 dx value. Here are the values. So f of 1, well, 1 cubed is 1. 1.4 cubed is 2.744. I'm just using my calculator here. This one came out to be 5.832. 2.2 cubed is 10.648. And 2.6 cubed is 17.576. And our dx was 0.4. If you multiply all that out, you add that and multiply it, you are going to get this. Well, this is going to be 37.8 times 0.4, and your final answer, 15.12 square units. Let's take a look at this Riemann sum now. Given the function 4 over x, and we want to break it up into 3 subintervals. All right, so if we're using equal lengths of 3 subintervals, what would the value of a right Riemann sum approximation be for this integral right here? Get used to the notation. We're going to start at x equals 2, and we're going to end at x equals 9.5. It does say round if necessary, and this is a lot of decimals. We're going to round it 3 decimal places. Graphically, this is what we have. We are going from 2 to 9.5, right? And if we're breaking it into 3 subintervals, well, how do we figure out the delta x, the change in the x? Well, we said that was going to be b minus a over the number of subintervals. So in our case, this is going to be 9.5 minus 2 all over 3. And if you do the math there, you're going to get 2.5, 2.5, which means our delta x is 2.5. So if you go 2.5, right, so this is going to be 2.5, the delta x, 2.5 the delta x, and 2.5 the delta x. That breaks it up. You add 2.5, you add 2.5, add another 2.5, it brings you to 9.5. We are working on right Riemann sums, so we want to do this. We want to just to visualize. We want to go to the right side of our interval, right? So that's going to be, that's 4.5 right there. So we want f of 4.5 as the height. This right here is 7, so we want f of 7 as the height of the second triangle. And if we're using the right Riemann sum, well, the right side is 9, when x is 9.5, so the height is f of 9.5. Here's what it's going to look like. In order to solve this integral, the area under the curve going from 2 to 9.5 for this function, 4 over x dx, we're going to do this. We have 3 rectangles, so I need to do f of 4.5 times the dx plus f of 7 times the dx plus the f of what is it, 9.5, sorry, 9.5 times dx. Plug this in, well here, think about this. So you know that f of x is 4 over x. Well, if I want to know what f of 4.5 is, all I'm doing is doing this. 4, I plug it in where the x is, so 4 divided by 4.5. If you want to know what f of 7 is, well, it's 4 over 7. And of course, the last one, if you want to know what f of 9.5 is, well, it's 4 over x. So it's going to be 4 over 9.5. So this right here, this one is 4 over 4.5 times the dx. The dx was 2.5. F of 7 is going to be 4 over 7 times the change in x. Plus, when you plug in an x is 9.5, you get 4 over 9.5. And if you multiply that by the change in x, that would be the area of your third rectangle. Plug it all into your calculator, and since we're rounding 3 decimals, you should get this as an answer. This is what I got. We get 4.703 square units. That's our approximation using the right Riemann sum. Here we're dealing with a function f of x equals 5 ln of x. And we want to break that up into 4 subintervals. Well, this right here is the function we're talking about, and our n equals 4. And we're going to have equal length intervals, subintervals. So that means our dx, our change in x, is going to be b minus a over n. This notation here is saying we're going from x equals 2 over to x equals 4, and then we got to figure out what our change in x is, or our delta x. So here's 2, and here's 4, and I'm cheating. I mean, I have the graph right here just because, well, I'm not the neatest artiste, if you will. Let's find dx. 4 minus 2 is our interval, and we are breaking it up amongst 4 subintervals. Well, that means that each dx must be 1/2, 0.5. And that looks, as you can see here, you want to break this up into 4 equal subintervals. That makes sense. And if we're going to use right Riemann sums, we want the right side as the height of these rectangles. Let's figure that out. Well, the right side for this one right here, this is going to be f of 2.5, right? And then this height for this is rectangle 1, rectangle 2, rectangle 3, and 4. So for the next one, we have f of 3 is our height, right? And this one is going to be f of 3.5 is the height. And then for the last one, well, we are going to use the last endpoint there, f of 4. Those all represent the heights of our triangle here, right? The height right here. And that's the height of this one, the height of this one, the height of this one. And then, well, all of these are your dx. And that is how you get your base times height. And, well, we said our delta x was 0.5, right? And that makes sense because this has a width of 0.5 and a width of 0.5. They all have 0.5. So now, if we look over here, I decided to do it this way. It'd be easier to see. It's easier to read, of course. Well, let me see. So f of 2.5, right? Well, what is that? Well, this is your function. So think about this. If you were to plug in 2.5, this is what we're doing. It's 5 times the ln of 2.5. And then if you plug in 3, you plug in a 3 where the x is. You just keep substituting where the x is. So this is what 5 ln of 2.5 is, times 0.5, plus this would be 5 ln of 3 times 0.5. This is 5 ln of, I think you get the idea. And then this one would be this, 4 times 0.5. You plug these ln's into your calculator and you're going to get these decimals. Multiply them by 1/2, you're going to get these values. It says round to the nearest thousandth if necessary. Well, these are long decimals here, so if you go 3 decimal places, there you have it, my friends. All right, you may say, why so many examples? Well, I just want to make sure I've shown you so many varieties. Here's an exponential. You may see one of these, and I don't want you to get concerned. I want you to say, oh, I can go back and look at that example Messiano did. So here we go. We have 5 subintervals. This one is telling us we have an n equals 5. And if we have, there it is, equal lengths. Okay, when it says equal lengths, that's when we're going to do dy. I'm sorry, not dy. dx, our change in x, is going to be b minus a over n. In this case, get used to the notation. We're going from x equals 2 to x equals 3, so it's going to be 3 minus 2 all over our n value, that is 5. That's 1/5. Now I know how much people love fractions. That is also 2/10, which means it is 0.2, it's 2/10. So we can use the decimal, but I want to show you using the fractions not that big of a deal either. All right, here's our, so this is the graph right here. I didn't write it. This is f of x equals, I'm on a wrong problem here. That's 2 bases 2 raised to the x. Okay, so there we have it. On this graph, we want to know what is the area under the curve going from 2 to 3. And it's using midpoint Riemann sum. So here's a midpoint example. Well, the first thing we do is break up our intervals. We know we have 5, so here's rectangle 1, 2, 3, 4, 5. But how do we know what the subinterval? Well, the dx, that tells us what it is. And the dx here, the change in ex each time, is 1/5. So if this is 2, this is 2 and 1/5. This is 2 and 2/5. 2 and 3/5. 2 and 4/5. And guess what 2 and 5/5 is? That's right, 3. It's not that hard breaking it up into fifths. But let's go and use the decimals because that's what you're probably going to use anyway. And we did say over there that change in x is 0.2. So if that's 2, this would be 2.2. This would be 2.4. This is 2.6. And this is 2.8. And yep, that's 3.0. Now we're asked to find the midpoint Riemann sum, which means we're going to use the midpoint as the height. So right here, this is going to be f of 2.1. If you can see, this is 2.0 and this is 2.2. So what's the midpoint? Well, in between is 2.1. So the height, we're going to use f of 2.1. Now, if it's not that obvious, you could do this. Well, how do you find the midpoint? Well, you take 2.2 minus 2.2, and then you divide by 2, right? You take this endpoint and this endpoint, and then you divide by 2 to get the middle point. So that's how you do the midpoint, and you would do the same thing here. So this is 2.3 we want, which makes the height f of 2.3. This height is f of 2.5. This midpoint is 2.7, so this height is f of 2.7. 2.9. This one, the height is f of 2.9. Remember where the pause button is. If I'm going too fast and you're trying to copy all this graph stuff down, just pause, rewind. You know where those buttons are. Let's figure out what this is going to look like now to figure it out here. And based off of that graph, here we have, there's our function f of x equals 2 of x. So I'm not going to do all of them, but if you just do the first one here, if you want to know what f of 2.1 is, you plug in 2.1 where the x is. In this case, it's in the exponent. So f of 2.1 is really 2 raised to the 2.1 times 0.2. This would be 2 raised to the 2.3 times the dx. This is 2 raised to the 2.5 times the dx. 2 raised to the 2.7 times dx. Not dx. 0.2. And then this is 2 raised to the x value, which is 2.9, times the dx, which is 0.2. When you plug those exponentials into the calculator, you're going to get some decimals. When you multiply those decimals times 0.2, you get these values. And when you add them all up and you round those decimals to 3 decimal places, you get yourself 5.766 square units. When discussing upper and lower Riemann sums, I'm going to talk about inscribed rectangles and circumscribed rectangles. I just want you to remember what they mean. An inscribed shape, whatever the shape is a shape that is completely inside another shape. The circumscribed shape is going to be a shape that is completely outside of another shape. Here we have a triangle and a circle. This circle, well, the circle is completely inside the triangle because if you notice the vertices here touch and they're completely inside. That is an inscribed circle. It's inscribed inside the triangle. Circumscribed, well, notice how the triangle is completely outside of the circle, and you know that because it touches here at tangent points here. And so this triangle circumscribes this circle. Now regarding Riemann sums and rectangles, let's look at this example right here. This is f of x equals x squared. We're all familiar with that graph. And, well, depending on here, we were talking about left and right Riemann sum. Depending on the curvature, it all depends on the curvature. The way this curvature of y equals x squared goes, if you notice, the left endpoint Riemann sum is inscribed. Okay? And if you were to compare that with the same graph, y equals x squared, with the right endpoints, well, the right endpoints are circumscribed as they lie outside of the area under this curve, f of x equals x squared. And this, I used the word last video, overestimate and underestimate. Well, this is an overestimate, right? They're estimates, they're approximations, but this one's going to be over. You can see it's going to be a little bit over. Versus the inscribed, well, that's going to be a little underestimate, right? That's going to be a little less than what it should be. You can see there. And we talked about the midpoint being a better approximation for all of them. Regardless of the midpoint, when I'm referring to, so now we're going to talk about upper and lower sums. So as you can imagine, if it is if it's an underestimate, you're going to get a lower sum than what it actually is. And if it's an overestimate, well, you're going to get an upper sum. You're going to get something above what the actual sum is. Okay? And then somewhere in between the lower and the upper is the mid sum, which would be your midpoint. But you got to realize that it's not always the left endpoint being the lower sum and the right endpoint being the upper sum. Let's consider the curvature this way. Okay, here's an xy here and an xy here. And let's do something that looks like this. Here's my graph. And here's my graph. If you go for left endpoints on this type of curved graph, well, notice how the left side now is the upper sum. And if you were to use right endpoints, well, the right endpoints, right, say you want, are going to be the under or the lower sum, if you will. So I just don't want you to think that the lower sum is always the left endpoint, because as you can see, sometimes the lower is the right endpoint. And same thing with the upper sum. Depends. Depends on the curvature of the graph. Let's give you a little bit more formal, still straightforward, but more formal definition of upper and lower sum. Upper is a sum of the area of those circumscribed rectangles, right? The overestimate ones we talked about. And the lower sum, well, that would be the underestimate, the ones that are inscribed, right? And here, when you're asked to find, depends on where you're going. Let's just look at this example. If you're going from, what is that, -2? Say you're going from x equals -2 to x equals 3 on this graph. So on that interval, say the question asked you to find the upper sum on that interval between -2 and 3. Well, the upper sum, you want to make sure that you're finding the circumscribed. And the circumscribed may be the left end points, as you can see the way it's curving this way. But if you want the upper sum, you want the ones that are circumscribed, well, you may have to switch it depending on the curvature of your graph. So now notice on this side of the y-axis, my right endpoints are the circumscribed ones. So that's just, if it says upper sum, you may have to change which endpoints you're using for each rectangle. For the lower sums, we'll do that in red. The lower sums, you're going to want to make sure you're doing all the inscribed rectangles. Well, the inscribed, on this side, you would need the right endpoints. But then on the other side of the y-axis, if you want the inscribed ones, you need to start taking the left endpoints. I think that's pretty obvious. That's pretty clear right there. All right. So again, depending on if it asks you for the lower sum or the upper sum, well, determine which ones you need where, and then go ahead and take those heights and find the areas of those rectangles. Let's finish up with these two examples here. One finding an upper sum and one finding a lower sum, approximating. So this one says approximate the upper sum of this shaded region. Shaded region looks like it's going from 1 to 5 using rectangles of width 1. All right, upper sum. Which means if we're going to use width 1 and we're going from 1 to 5, that means, let's see how many rectangles we're going to have. It's going to give you 1, 2, 3, 4 regions. Now, if we're using upper sum, we need it to be the circumscribed ones. So for this side, it would be the right side. But then for the next one, it's going to be the left side. And then for the rest of that curvature downward, it's going to be the left side. Okay? Let's find the areas. Okay, rectangle 1, base times height. So we're going to do the f of x times dx. The f of x is the height, that's 5, and the dx is the width, that's 1. All right, the f of x on this one is also 5, and the width is 1, the dx. For this one, that is a height of 4, and like the other ones, it has a width of 1. And this one, we're going up to this number 2. That has 2 times 1, because that has a width of 1 also. These are all widths of 1. All right, well, I don't think we have to write this up formally. We can do this quick. We have 5 times 1 is 5, plus 5 times 1 is 5, plus 4 times 1 is 4, plus 2 times 1 is 2. We can add that up. What is that? 16. 16 square units is the upper sum. Now, how about an example with a lower sum, approximating a lower sum. All right, so here's another one, and it says approximate the lower sum of the shaded region using rectangles of width 1. All right, width 1 makes it easy to work with here. We have, we're going from 1, in this case, the shaded region is going from 1 to 4. All right, and well, widths of 1 mean 1, 1, that means we have 2. I'm sorry, not 2. We have 3 shaded regions, 3 rectangles. Well, if we're doing the lower sum means we want to have all the inscribed in each of those regions. Inscribed, sometimes, so in this case, it's the right, and in this case, it's the left Riemann sum on this side, on either side of 2. All right, well, let's find this first rectangle right here. That one is going to be, well, the height is 2, and the width is 1. That's 2 times 1. The next one is the same one. That has a height of 2 and a width of 1. So for this one, we have 2 times 1. And for this last one right here, well, the height, as you can see, is 3. And of course, the width is the same. It's 1. That's 3 times 1. So if you have 2 plus 2 plus 3, that gives you 7. 7 square units is the lower sum approximation.